Hi, everyone. So actually, I didn't know about the other talks that just happened with Casey and Rupcha, but my talk is a bit of a mashup between energy and verification. So I think it's very in theme with today's talk, which I'm pretty excited about. And I'm glad that they went first, because it gave a pretty good primer of a lot of the stuff I'm going to be talking about. So this talk is aptly named Standards We Love. The subtext is for assuring and verifying safety critical system. I work for a company named Adelard that is in London, UK. So some of this talk is UK-centric, but applies internationally. I'm American, by the way, if you're wondering why I don't have a British accent. So sorry about that. I'm a consultant, a research consultant, actually, and that's a bit of a vague term, but I do quite a few things that all tie in together. I evaluate, design, specify, and verify safety-critical systems. I carry out safety and security assessments on a lot of safety-critical systems, again, and I help produce standards and guidelines for safety and security-related applications and development. A little bit of background about myself. I finished my computer science at UCL, which is University College London, in 2017. It was on temporal logic model checking and verification of software system, which Rupcha gave a very good primer on today. I'm not going to be talking about that, though. As a PhD student, I did collaborate with Microsoft Research Cambridge to create and extend a tool, a model checking tool that I created called T2 to support temporal property verification. I did CTL, LTL, and CTL star. Again, if you were here for the talk earlier, you probably remember what those means. And I focused on verifying things like Windows device drivers to find various types of errors. And now I work on safety critical system, which uses very different technologies from what you're probably used to. Like if you work for your average tech company, like whether you're at Google, Salesforce, Facebook, or Twitter, and that's for a very good reason. If you look at the definition of what a safety critical system is, it is a system whose failure or malfunction may result in the following outcomes: death or serious injury to people, loss or severe damage to equipment, and environmental harm. This is different from what a safety verification property is. When I say safety in this talk, I actually mean like people's lives. The consequences of a safety critical system malfunctioning isn't the same as like your Messenger app or Instagram or a website going down. I think there was a big AWS outage yesterday that happened in the UK, but still, that likely isn't going to kill hundreds of people at the same time. And companies like Adelard exist to assure the safety of various critical systems. We work on aviation, nuclear energy, and that's actually our largest sector, and I'll be focusing on that today, automotive and rail, and we work on defense, medical, finance, and most recently, autonomous systems. We actually won a grant recently to work on verifying self-driving cars or assuring self-driving cars, and that's actually a minefield on its own. So we're working on a lot of different things. So you probably know what formal verification is at this point, because we did have a talk on it. But to give you an idea of why we care about it, I think this quote is always a really good quote to bring up, and you've probably seen it before, which is program testing can be used to show the presence of bugs, but never to show their absence, by E.W. Dijkstra. So it's always really good to keep this in mind. So some of you might not know the actual definition of formal verification. You might have implied it from some other talks. But it's the process of establishing whether a system satisfies some requirements using formal methods of mathematics. And that definition is a bit vague on its own. So I wanted to give an example of the process of formal verification using a specific technique called model checking. If you had a model checking verification tool, this is what the process would look like. You would first take your code, and you would formally model it again in some appropriate framework. And then you would take your requirements, and you would formally specify them in some expressive specification language. Temporal property is an example of that. And then you would exhaustively explore a system's mathematical model against a specification, and that's what model checking is. And finally, you do your analysis. So if not all the specifications were satisfied, you analyze the findings and the consequences. And this is a process that people generally refer to in both industry and academia when they say formal verification. And you can replace this model checking bit with any technique. It could be abstract interpretation, theorem proving, and so on. So in academia, there's a lot of focus on models and the checkers themselves, so this bit right here, and sometimes the specification as well. But in industry, we actually spend a lot of time on the analysis stage. So I'll get more on that later on in the slides. So at first, I wanted to talk about my experience in academia versus industry. The issues that we face in industry differ a lot from those we face in academia, which is why we have these different focuses that I talked about in the previous slide. So I created this pie chart. It's not reflective of any studies, just my own personal experience. So I spent about 5 to 6 years in academia, and I didn't find that many bugs, but relative to an academic, I did find quite a few. And in my 1 year of industry, I found significantly more bugs. So the bugs that I found in academia are just a fraction of a percent what I see every day in industry. And that's because in academia, we're very invested in producing more nuanced and expressive formal frameworks, despite the lack of scalability and applicability. So the bugs so the bugs found are very specific and rare, and especially if you can't run a verification tools on things like 10,000 lines of code or more. In industry, we have industrial-level formal verification frameworks that are pretty good at finding thousands of bugs and millions of lines of code, but the bugs can be a bit shallow, and our issues really regard how and what bugs should be fixed and their impact on the security and the actual safety of the system. So given that we can't even get our printers to work, our apps crash, and I'm telling you about these thousands of bugs that I'm finding, you might be wondering, well, how are we all not dead yet? I mean, it makes sense. So that's what I'll be talking about today. I'm going to be focusing on 3 points. How software safety critical systems is assured, verification of a specific type of component that is one of the biggest challenges in the nuclear industry, and that's smart devices. And actually, Casey talked about smart devices in the grid. And finally, I'm going to be talking about lessons learned from standards, guidelines, and processes used in safety-critical verification and assurance. In general, I would like to talk about all of the safety-critical systems that I mentioned, but I can only talk about one, so I'm going to be focusing on the nuclear industry, because that's what we do the most of, or what I do the most of. But you can generally infer the process of the others from these slides. So, a bit of physics 101. This is kind of what's inside a nuclear power reactor. You have something called a containment structure. And in that containment structure, this is where the nuclear reaction is actually happening. You have a reactor vessel, and these rods come up and down and control the nuclear reaction that you have. And these orange lines actually demonstrate the water that's in the system. So there's water flowing through here that's getting hotter and hotter with the reaction. And you have a pressurizer. The reason why you need a pressurizer is because water boils and evaporates under different temperatures, given different pressures. So you have this pressure in the system that's making sure that no water is being evaporated or boiled. So the point of this reaction is to actually heat up another water system. In this system, the purpose of it is to boil the water, or for it to evaporate, really. And so you're creating all of this steam, which goes to a turbine, and then circulates to a generator, and then goes on to your city. Actually, I'm really happy that Katie gave her talk, because I don't have to explain the rest of the grid and how that works. And any water left in the system is condensed back and it's kind of recycled. Please don't ask me any more questions about this. I'm not a physicist. Luckily, we do have physicists that know more about this than I do. But the important thing to know is that every bit of the system is controlled by something called a smart device. So you have it here, the reactor vessel. You have something that's looking at the pressure. You have something that's controlling the temperature. Same with this other water system as well. So What are these smart devices? Well, they're really just embedded devices, and a lot of times they look like this. They're not this huge. They're usually about this tiny, and they vary in functionality. They're written in C and assembly from the devices that I look at, and they can include things like FPGAs, which is a field programmable gate arrays. If you don't know what that is, don't worry about it. There's usually no underlying operating system. They're interrupt-driven, which means that the software directly interacts with the hardware. So there's no operating system to manage the interrupts or memory for you. It's all done exclusively and manually through your code. There's other tricky bits as well, which is the use of pointers in C, and communication protocols. And the use of compilers vary depending on the processor and the hardware. I think something that I had the wrong impression of when I was working in academia is that everything is standardized. We have GCC and LVM and Intel x86 because that's what we should use. But it turns out these companies actually all write their own compilers, and they all implement their own architectures. And that's actually a minefield if you're thinking about it from a verification point of view. And they're really not written to be verified either. There's rarely specifications and requirements found. And that's because the nuclear industry is a very small customer when it comes to buying smart sensors. They're everywhere in the world. They're used in industrial farms, they're used in factories, they're used in a lot of places that you wouldn't think of that aren't safety critical. And these are the kind of companies they tailor for to make more money for. They don't see a point in writing verifiable software for one very small customer. And finally, they can range between 10,000 lines of code to millions lines of code. Yeah, the device is very tiny, but they're actually very capable as well. So they're really just embedded applications. They're pretty good at doing things like reading and writing data, setting timer registers, and reading input captures, that sort of basic stuff. And I wanted to give you a feel of the kind of code that I spend all of my time looking at. So there's something called ARM C51, which is a C extension. It's not standardized, as usual. And it has special data types, one's called SFR and SBIT, that are used to customize a compiler to the target processor. So this is a toy example. This isn't an example of what you would actually see in a smart device. But just to give you a feel of it, here I am initializing some ports and registers using the SFR and SBIT, depending on the processor that I have. You have to know the hardware pretty well when you're writing this kind of code. And here's a timer interrupt. A timer interrupt is an interrupt that's triggered every X amount of seconds. And most of the functionality of these smart devices is actually implemented within the interrupt itself. You don't have a nice control flow. You just have interrupts being triggered every few seconds, and the function for the specific interrupt does some sort of specific bit that all works together. So here, I'm initializing some chars, temp1 and temp2. I'm writing some data to a register right here, writing data to a port, reading data from a port, and finally, I'm setting other interrupts to be enabled and disabled using bits. It's kind of very different if you are programming using modern day sort of modules, abstractions, library. It's like things have advanced quite a bit for normal developers, but if you're looking at sort of smart devices, you're still kind of programming like it's 1970. So you might be wondering, well, why use these systems altogether? C is a fantastic way to shoot yourself in the foot. Well, that's actually a pretty good question. So you have to remember that a lot of nuclear power plants were built in the 1970s. And they used analog sensors. A lot of them did. And now those analog sensors are no longer found for many reasons. They're too expensive to make. They're unmaintainable. We have software, so why should everything be analog? So I think you'd rather replace something in your nuclear power plant that has software in it rather than have the nuclear power plant fail altogether. So that's a pretty good reason to have it. You have improved functionality. Microprocessors and microcontrollers give you a lot of power now because you now have better accuracy, calibration, and diagnostics. If something goes wrong, you can look at logs. You can trace it back. And they're configurable, but not programmable. And that's really great. If you actually want to go and like hack into this device, it's actually very difficult to do. You can't reprogram it. It's tricky. And there's a lot of sort of user password implementations that allow you to configure it, given that you have the right access. And finally, it's pretty efficient and fast, as with why most people use C, really. And you can actually find these anywhere. They're industrially embedded devices. We call them commercial off-the-shelf because you can just buy them as is and purchase them without any specialized orders. They perform a very defined and simple function. So you have a temperature transmitter. All it does is it measures the temperature, pressure transmitter, or voltage regulators. But as it turns out, we can't just install smart sensors in any nuclear facilities as we please, which is a very good thing, actually. So in the UK, we have something called the Office of Nuclear Regulation, and it exists to make a lot of decisions regarding who can use nuclear and how. There's an equivalent in every country. And then you have the IAEA, which you've probably heard of, which is an international agency that promotes a peaceful use of nuclear energy. And you've probably seen them in news with regards to policies with, who can have a nuclear program, dismantling a nuclear program, all of those things. And each year they organize workshops to talk about a lot of things, including the assurance of software systems and how they should be addressed. So this is from one of their workshops in 2017. One of the things they talk about is what to prioritize. And they noted that one of the most important things is that we need to focus on justification of smart devices and how we can assure them. Adelard, the company I work for, actually works with these agencies to promote standards and guidelines that would make our nuclear power plants safer. More specifically, we contribute a lot to the process of smart device justification, which I'll talk more about today. And just to note, the most recent IAEA guidelines actually includes work from the partners at Adelard, which we're pretty excited about because we've been pushing some things that we think really should be included in guidelines. So the ONR, which is the Office of Nuclear Regulation, has something called the Safety Assessment Principles, which are defined as the primary principles that define the overall approach for nuclear installations in the UK. So of course, part of that is a justification of computer software. The justification of software requires 3 aspects. That's something called production excellence, which I'll be focusing on more today. And the definition of that is a demonstration of excellence in all aspects of production, from the initial specification through to the finally commissioned system. And then you have compensation measures, which is if you have any gaps that are identified in your production excellence, it means you have to compensate for them. Finally, you have independent confidence building measures, independent and thorough assessment of safety systems fitness for purpose, which means that you need an independent assessor to tell that your system is also fine. If you think it's fine, I mean, that's great, but you need independent assessment as well. So the way that these are satisfied is through a lot of things. I'm going to give you some boring definitions of what they mean, and then talk more about how we try to satisfy production excellence. So the definition of production excellence, and for you to be able to satisfy it, is application of best design practice consistent with accepted standards for the development of software for computer-based safety systems. Basically, that's what that means, is that you're following some standard. There's some best practice that you can prove that you're following and show that you fulfill all the requirements. So the standards that we mostly look at in the safety critical industry is IEC 61508. This is what we call the golden boy standard because it covers all safety critical system, and a lot of people have to abide by it internationally. So IEC is sort of international standards. You have more specific standards, which are industry specific. So you have 61513, which is for the nuclear industry. You have 26262, which is for automotive. And you have DO 331, which is for aviation, and they actually have the strictest standards for obvious reasons. I really hope that most people follow them. The second thing that you need to do is follow a modern standards quality management system. You might be aware that your own company actually has a qualification for ISO 9001. And what that means is that you need some traceability. right? So if you use things like version control, whether it's through GitHub, ClearQuest, or ClearCase, that's great, because there's some traceability of your documentation. You're managing versions that you have, whether it's of documents or of code. That is something really important for satisfying production excellence. And finally, you need a comprehensive testing program, which isn't new to many of you either. The second bit is independent confidence building measures, which is the complete and diverse checking of the production software by an independent team. So this involves getting an independent team on board, which is usually Adelard is that independent team. And we do things like take your system, we apply formal verification on it, static analysis, and testing as well. It's important that you have an independent testing team to come on board and check your system for you. So I mentioned that production excellence references standards to be followed, and I'm not going to bore you with thousands of pages of standards. So how relevant is formal verification in assuring these systems? So here's an excerpt from 61508. Again, it's one of the most important safety standards applicable to all safety-critical industry, and the standard has multiple parts. But this is a table of contents of the software requirements bit. And the way that 61508 views software is sort of in a development lifecycle point of view. So if you notice here, it breaks them down in software safety, requirement specification. This is when you're writing your requirements. It talks about the validation plan. So how are you going to validate your software when you implement it? It has requirements about software design and development. So this is where it breaks things down further to software architecture design, tools and programming languages that you're using, detailed design and development, code implementation, software testing, software integration. There's a lot of requirements to unpack here. And then you also have other things like software operation and modification procedure. What would you do if you need to modify your software, and how is that traceable? Software system validation, modification, verification. And actually, when they talk about verification here, they don't really mean formal verification. They're talking about, in general, verifying your software. And of course, formal verification is a part of that, but it's not all of it. So each set of lifecycle requirements has what's called TNMs, and that stands for techniques and measures. And it's techniques and measures are techniques that you need to carry out for each step of your life cycle. And they provide you some table which tells you, OK, these are the techniques that you need to check off. And in this specific case, if you look at the software design, development, software module, testing, integration, sorry, it goes on for a while. Here, they mention that you need to do dynamic analysis and testing, functional black box testing, performance testing, model-based testing, interface testing, and then a few other, and then they talk about formal verification. You don't actually need to do formal verification all the time. It depends on the safety integrity level of your system. So we actually categorize safety critical systems to 4 categories because they're not all equally as critical or equally as important. So SIL 1 is the lowest. SIL stands for safety integrity level. A lot of times you won't need to do formal verification for that kind of system. The highest integrity level is 4. And in this case, it's saying it's recommended that when you have a very critical system that you carry out formal verification. So here's another table from the standard saying that static and dynamic analysis are required by most safety integrity levels for the verification stage of the development lifecycle. Now that makes sense, right? You're at the verification stage, you need to do some sort of analysis for most integrity levels. But here it's referencing to table B.8. So let's have a look at that and see what they mean by static analysis, what's required for us to carry out. So, boundary value analysis, OK. Checklist, I wouldn't really consider a checklist static analysis, but I guess in this case the standard does. Control and data flow analysis, a lot of us might be familiar with that here. OK, fair enough. Error guessing and walkthroughs, I think that's a bit strange to put here because you wouldn't really consider a code review static analysis. I mean, technically it is static, but like I wouldn't consider that static analysis. You have Symbolic execution, which is not static analysis. I wouldn't say that it is. I would say it's a formal verification technique. Design review, static analysis of a runtime error behavior, which I think is a cyclical definition. If you're saying this is what static analysis is, and then you say it's static analysis, I don't think that helps anyone. And then you have worst case execution time analysis. Again, I wouldn't say that's static analysis. So if you're familiar with formal verification or static analysis in the case, you may have noticed that terminology doesn't really make sense, and it doesn't really add up. And it doesn't really match our modern terminology when we talk about these kind of systems. Like, with Roops, like I said, gave a pretty good primer on verification terminology, and these don't seem to really add up to the kind of techniques that we carry out. Well, if you look at the paper references for these techniques, that might give you a clue of why these inconsistencies are here. So these are some of the main references for static analysis and verification. So we talked about model checking today by Clark, Grunberg, and Peled, which is a pretty iconic book about model checking. We have systems and software verification, model checking techniques and tools. OK, more model checking, great. And then Spin Model Checker, it's a classic model checker that was created. Actually, I think it was before 2003, but this is a paper reference from 2003. And then you have using symbolic execution for verifying safety-critical systems. So these papers have all one thing in common, is that they're pretty old. Formal verification has come a long way. But all of these papers, the latest one you can see is from 2003. But they are pretty similar to verification, but they just don't target our system. Even this last paper isn't looking at the same safety-critical system that we usually look at. And surely verification has come a long way in 20 years, and maybe standards are really slow to update. Well, that is true. Standards are not perfect. They are pretty slow to update. But it's important to note that all standards they're a consensus-building exercise. It's just a particular group of people who got together in a specific moment in time and decided this is how we should verify safety-critical systems. So the next day, what they decided might get outdated. And what works well for predictable systems, when we have this idea of standards, when the idea of policies and standards came about, technological systems weren't kept in mind. So defining a standardized way to build software is really difficult. And software systems and verification technologies advance way faster than standards updates. Standards can update once every 10 years, once every 20 years. It depends on the standard. It depends how fast the committees work. So they can get outdated pretty fast. And interpreting a standard against each unique software system may pose difficulties. So for example, 61508, sorry, I have a typo here, provides no guidance on when and how to apply these standards, these verification techniques, and it's a checklist approach. But the thing is, all of these formal verification techniques can only be applied to specific system. Depends on the property that you're looking at. It depends on the language that you're coding in. So you can't just have a checklist and say, oh, I've done this and this and this. It really depends on the system that you have, and standards don't really guide you in that direction. And even if software could be standardized, software will still have bugs. It's really important to know that even if you follow these standards, you will still have bugs in your software. So it's not the end-all, be-all of what we should be following. But on the flip side, for the specific devices that we do look at, these smart sensor, not much has changed technologically in 20 to 30 years, which is really unfortunate. Industrial verification tools lack property-driven techniques, and when I say property-driven techniques, is you being able to write specification to reason behaviorally about your program. State-of-the-art formal verification techniques, and that's usually all coming out of academia, they assume a lot of things that we can't make assumptions about, like you have a standard C compiler. GCC or LLVM are academia's favorite things to look at. Assume standard architectures, Intel x86 or ARM. Again, even in just my year, I have yet to come across an Intel x86 embedded device. They assume you have an underlying operating system. That's something I really took for granted when I was in the verification community. I just always assumed, hey, there's something doing everything for me. But for these devices, there's nothing doing anything for you. You have to do everything yourself, which is really painful. You you take for granted the scheduler, your memory management. These are all really nice luxuries to have that I think we've taken for granted since 30 years ago or so. And there's little support for embedded devices in the verification community. And actually, we don't have any support for interrupt-driven systems. That's not something that people look at or even think about verifying. And it's not scalable beyond 10,000 lines of code. And the minimum amount of code that I've looked at was about 12,000, and most of them are in the hundreds of thousands. So scalability is a huge issue for us. But let's look at what some academic papers look like to give you an idea of why this is problematic for us. So I only picked out a few, but I want to talk about this one, analyzing memory resource bounds for low-level programs. This was an ISMM in 2008. They say that they do memory resource bounds inference for assembly-level program. OK, great, because the kind of code that we look at is very close to assembly. They do a fixed-point analysis and formalized inference system for a small assembly language. OK, this is where things get a bit tricky. When they say for a small assembly language, they really mean a subset of some assembly language, like really a toy example. And that's not something that we can work with. And when they say a formalized inference system, that means that there's a lot of manual work required for that, and it's not really automated in the way that we'd like it to be. And it supports only a subset of standard C. So the example of code that they mentioned in the paper that's analyzed, is this bit right here. This is not memory safe. If it's not obvious, please don't code like this. But again, this is very different. Even if this is low level to you, like if you remember a few slides back, we go like lower than that. We're actually interacting with the hardware. So yeah, they say, yeah, we're doing it for embedded devices, but I mean, not really. So it assumes standard C. It assumes an underlying operating system. There's no interrupts. And unfortunately, most academic papers are in line with this type of analysis, even if they say, we do embedded verification for safety-critical systems. They don't really. I've read through a lot of these papers when I started my job, and I was very disappointed. But there's some work that is beneficial, right? There are some people who do try. This is an older paper from 2001, analyzing memory resource bounds for low-level programs. So I actually really enjoyed reading this paper because it was actually very relevant to the work that I do. So it did static analysis for an interrupt-driven Z86-based software with hard real-time requirements. This is great, right? It's a great start. It's one of the only papers I've ever come across. If you know any other papers, please send them to me, that talk about interrupt-driven system. Z86 is not a standard architecture that everyone assumes that you're using. And the whole idea is to do stack analysis and interrupt latency analysis. OK, these are the kind of properties that I'm very interested in. But then if you look at how they do it through modeling the program counter and the interrupt mask register. So what they're doing is that they build not only a control flow of the code that is being used, but they actually have to now reason about hardware bits as well. They have to model the interrupt mask register and the program counter along with the software that's being used. And now your problem of exponential state space is even bigger than before. And the whole point is to record whether interrupts are enabled or disabled. So this is actually targeting a very small, niche property, and we're interested in a lot more properties than that. So the idea is to build a control flow graph in which each node represents, the state of the program, the PC, and the interrupt mask register. This is, of course, a very manual process, and it's not scalable. And their example here, it only covers 1,000 lines of code or less. And that's pretty far from hundreds of thousands of lines of code or 1 million lines of code. But at least it has potential for exploration, right? You can say that, well, at least there's some strategy out there. But smart devices are being installed and replaced every day. We really only have a few months to sort of verify it, sometimes less than that. Sometimes it's an emergency and it needs to be evaluated now. I can't sit here and model the architecture of every single processor I come across, look at the compiler, and then model the hardware with the state space of the software, right? That's not very feasible. So we need a short-term solution. So we have two issues. how do you manage to meet what's required by these standards, especially that we don't have academic work to help us? And how can we adopt new techniques to help us assure our systems, especially when standards don't reflect them? So at Adelard, we use what's called the safety justification triangle to incorporate the software properties we're interested in against these standards. Recently, the IAEA has actually adopted this approach in their guidelines, which is fantastic, because it's a much better way of looking at properties and formal verifications for safety-critical systems than the checklist approach that I showed you earlier, which is like, have you done this? Have you done that? You know, they don't ask anything about why you did that and the results of that formal verification technique. So we view verification of properties in 3 different categories. You have a property-based approach, and this is really focusing on the behavior of your program. So you have functionality, accuracy, timing, failure integrity, non-interference. And then you have vulnerability assessment, which is data races, deadlock freedom, stack and buffer overflow, memory safety. And then finally, you have coding standards and complexity metrics, and this has to do with this standards compliance, really, following. I didn't show you, I just showed you the table of contents, but actually the standards say a lot about the kind of code that you need to have. Some of you might have heard of MISRA C, which is a standardized C that's used in aviation. It's like a subset of C that you have to use when you're doing software for airplanes. So things like that you have to follow. It's mostly syntactic. I think a better example is a linter. Some of you might have used PCLint, or if you program in Python, Python has a lot of linters as well. That tells you syntactically you shouldn't do this because it might lead to these other issues and so on. So that's what standards compliance is. So we take these categories and our strategy is to engineer our own tools. So we start with available tools. In academia, we have a tool called Pharmacy. It's compatible with standard C, but it's a very lucrative open source framework for verifying behavioral properties. In industry, there's industry-level verification tools like QAC, Polyspace, CodeSonar. If you have not heard of these tools before, do take note. They're actually pretty useful if you're interested in sort of automated verification on the code that you're running. But they have limited properties. They look at what we call runtime errors, so like data races, uninitialized variables, that kind of stuff. It's not really looking at the behavioral and functional aspects of your program. And surprisingly, both Pharmacy and all of these other tools are based on abstract interpretation. And actually, one of the things that I learned going into industry is abstract interpretation is one of the most scalable formal verification techniques. If I had known that, I wouldn't have done my thesis on model checking, but that's fine. I can always learn. And we engineer these tools. So we do code transformation to reduce programs to standard C, right? That requires some syntactic and semantic reasoning. And we develop plugins for Pharmacy, and that's what I'll actually be talking more about next. So this is the architecture of Pharmacy, which is why I say it's a pretty cool environment to do formal verification in. There's a lot of formal verification environments. But Pharmacy has like what's called the main kernel. It's open source. You can hack it, but you don't need to. And this main kernel has its abstract interpretation techniques in it and the abstract interpretation domains. It also has AST implementation, so you can manipulate the AST through it. And AST is an abstract syntax tree. And then it actually extends to what's called SIL. SIL is an intermediate language for C, which allows you to reason about the control flow of C. If you use LLVM as a compiler for C, you might have heard of the LLVM IR, which is the intermediate representation. This is something very similar. It's just a nice, almost abstraction that allows you to reason about the control flow of C without sort of digging into the assembly level meaning of it. And then on top of the Pharmacy kernel, you have plugins, right? So there's an API that you can use to interface with this kernel. So that way, when you're implementing a tool or a plugin extension to Pharmacy, you don't actually have to compile the code from scratch. You don't have to dig in and figure out what they're doing. Actually, in the formal verification implementation, you can just call these really useful verification sort of functionalities to implement your own verification technique. And there's huge libraries of plugins that people have developed for Pharmacy that might do something really useful for the kind of code that you have. So it's extensible through new plugins that may use functionalities provided by either existing plugins, you can build off other plugins, and the kernel, and allows for plugins to be written with relatively little effort. The plugins are written in OCaml and passes an ML file through the command line. So it's really nice, actually. You can just write almost a script-like file in OCaml and just pass it through pharmacy, and it will immediately start running that against this kernel, and then you can run a new sort of verification technique that you implement. So for us, we actually have to do a lot of that because we're constantly getting new devices, new architectures, new C extensions that we have to tweak the plugins that we have to make it work. So we can verify a few things in pharmacy. So it's really great because it allows for rapid prototyping and deployment. So in production, we have things like stack analysis, resource analysis, and functional analysis. This is exactly the kind of solutions that we're looking at, because otherwise we won't be able to keep up with the demand of the installation of smart devices or replacing smart devices. So in a ways, the same idea that I've used at an academic level, I'm now using at an industrial level, just more adapted. So even if academic tools did solve our problems, I mean, that would be great if they did, but we're just getting started. So even if you have a nice list of results, you need manual inspection and judgment is required for every single set of results that you get. And we don't get just like 5 bugs. We get like thousands of bugs that we actually have to inspect. So our formal verification tools can just say, here, I found 1,000 bugs for you. We actually are required to go through every single one of them and sentence them. And this is what we call the sentencing phase. It's actually manual labor. So no automation in formal verification will ever make this go away. And that's because we have a lot of questions we need to ask. This is sort of a social political questions as well. This one is pretty easy. If you've used any static analysis tools, you can always ask, are the bugs false positives? Rufsha talked earlier that if you have an abstraction, you're sort of over-approximating the state states that you have, so the bug that you get actually might be a false positive. Have the bugs that have been found, are they relevant to the safety and security of the system? A lot of time, these standards only care about safety or only care about security. You actually have to look at the bug and say, oh, OK, does this affect the safety of the system? Right? We talked about modular components earlier. Like, can you prove non-interference between the safety bit and like this LCD display? You might have a bug in the LCD display, like here, and the standards wouldn't care. It says, OK, well, it doesn't affect the safety for all we know. So it's fine. Leave it. Which class of bugs are more critical than others? Right? So if you have a lot of bugs that you need to look at in a short amount of time, do you look at data races, right? Do you look at the behavioral requirements? What is more critical at that point of time for your application? What is the probability of an actual bug occurring, and what is the acceptable level of failure? This is actually tied into the safety integrity level. Safety integrity levels aren't random. They're actually tied to the probability of failure, the minimum probability of failure for your system. So for a SIL 4, again, which is the most critical, the probability of failure needs to be way, way lower than SIL 1. SIL 1, there's an acceptable amount of failure. Usually, they don't really care if something goes wrong that much, because it's usually not installed in a place in the nuclear facility where if it goes wrong, things will blow up. That's usually sort of the idea behind SILs. And can testing and field data demonstrate infeasibility of a bug? So my favorite example to give on this is that we recently had a device that had 6,000 data races, which from earlier talks, you saw that a data race took out the electricity for the whole Northeast. It's an example that keeps coming up. So you're looking at this piece of code, and you're like, OK, so these data races are completely legitimate. They're not false positives. But this device has been running in the field for 10 to 20 years, and no errors have ever been reported. What do you do about that? I mean, I remember being a computer science student, and my code was not meant to be working, but it was. So it's like, do you leave it? Do you submit it? I don't know. I'm sure a lot of you still run into these errors today. So what efforts are required to repair a system, right? So if it's significant efforts and you have to take down the system to repair it, but then this smart device that you're looking at has been operating fine for 20 years. Is it a probability thing? Can the bug really happen 1 in a million years? I mean, you see it. It's actually very difficult because these are real-time devices that you can't always predict when the bug will happen. And do the repairs themselves pose a safety and security threat, and what is the impact? I've been in a lot of cases, again, when I programmed, where I would fix one bug and be like, yes, I chased it down. This is it. I've been, pulling my hair out, and then 100 more bugs come out afterward. And you're like, no, that was just, that was just a symptom. There's a lot of other bugs I need to go through, and we have to worry about that. We can say, okay, well, this is a bug. Well, what if we fix it? What if more bugs appear in the system? We have to think about the implications of every change that we make, which is why the standard focuses a lot on changes in your system. So verification is actually really a small part of what we do. We also look at hardware verification, specification correctness, right? Like, can you imagine writing precise and correct specifications for these devices? It's very difficult to do. It's always been an open problem to write correct specifications. And then you also have to do standards compliance. You also have to look at where the smart device is being implemented and the system as a whole. There's a lot more to think about than just the verification of code. So you might think, well, thank God I didn't work on safety critical systems. I don't have to think about any of this. But these concepts all tie into software dependability. It's actually all the same concept phrased differently. And each of you, if you develop any sort of system, you should care about software dependability. And software dependability consists of 3 concepts. There's attributes, threats, and means. I'm only going to go through the list of attributes, really. So you have availability, readiness for correct service, reliability, continuity of correct service, safety, absence of catastrophic consequences on the users and the environment, integrity, absence of improper system alteration, maintainability, ability for a process to undergo modifications and repairs. So you've actually heard all of these concepts before, just in a slightly different context. So the standards and the processes that I brought up all address these aspects and ensure the dependability of your software. It just might be phrased in a slightly different language. So the questions I discussed earlier are all difficult to answer, and our very small community is often left to its own devices. And we're really trying our best, but those in academia and industries, other industries, not the safety critical industries, don't consider these issues. Yet the impact of our community affects your everyday life. I mean, you probably flew a plane here, or drove here, or used a train. We're using electricity in the room right now, right? This is affecting your very life, like every second, yet none of us really think about it. We're always thinking about what's a new framework, what's a new language. I mean, I'm constantly overwhelmed by the new platforms that come out every single day, yet none of them care about safety critical systems. So I invite you to consider 3 things. The safety critical systems in the scope of future technologies and frameworks developed. If the appropriate technology exists, it will be adopted, even if standards don't catch up in time. People who assess these kind of devices know about them and can use them to their benefit. Recognize that what safety entails is always evolving and will in fact affect our views on system dependability and security. Verification is just a small piece of that puzzle. A good example of that is that now we have autonomous systems everywhere. Right? What does that mean for safety? What does that mean for assurance and verification? Right? So our idea of safety isn't static. We actually change the standards to keep up with new technologies. And that standards and guidelines already exist to increase system security and safety. Applying best practices wherever applicable will promote system dependability. So it might seem really daunting to pick up 61508 and go, let's see what this is about. I mean, it's nothing that any of us will ever do. But the amount of research and work that has gone into these standards actually could really benefit the whole technological community, because they talk about things that we don't think about till later and vice versa. Right? So you might be surprised what you can learn from a standard or a guideline for a safety critical system. So I hope you learned something today, and if you have any questions, please don't hesitate to ask. This is my Twitter handle, so in case you'd like to reach out at a later time, I'd be happy to talk, I'd be happy to chat, and thanks for being here.